Good morning, all of you. Today class, I will discuss this problem based on the vector space for any vector u equal x1, s2, x3, and another vector v equal y1, y2, y3 belong to R cube, and one of the scalar a belong to real number. Let us define it is the vector addition of two vectors u and v. They define like this: x1 y1 plus 1, s2 y2 plus 1, s3 y3 plus 1. And also the scalar multiplication of this vector is ax1 plus a minus 1, ax2 plus a minus 1, ax3 plus a minus 1. We here prove that R cube is a vector space over real number under these two operations. Okay. For this question, we want to check 10 axioms. If 10 axioms are satisfying, then we can say that this R cube is a vector space over real number. Okay. Let me check the 10 axioms. Then we can easily show that this is a vector space. Okay. These two vectors are in R cube. Okay. First axiom is a closure property of addition. For this, you take two vectors, let u equal x1, x2, x3 belong to R cube, and also v is another vector. You will by y1, y2, y3 is both are belong to R cube. Okay. First, you want to check the closure property. For this is the vector addition of two vectors u and v is of the form x1 is already defined, x1 plus y1 plus 1, s2 plus y2 plus 1, s3 plus y3 plus 1. Is it okay? So, here each of these values is a real numbers. Then this addition also real number. At one, then again is real number. This is also real number. This is also real number. Therefore, it is belong to R cube. Right? This shows that it is this vector addition satisfying the closure property. Okay. Right. Therefore, R cube is closed under this vector addition. Okay. Next, we want to check the second axiom. Second axiom is the commutative for addition. For this, you want to take two vectors again. Is x1, x2, x3 is y1, y2, y3 belong to R cube. Okay. The commutative property saying that your claim is you want to show that this vector addition equal to v that represent u. Right. First, you take this u vector x1, x2, x3. It's a vector addition y1, y2, y3. So this addition is already defined: x1 plus y1 plus 1, s2 plus y2 plus 1, x3 plus y3 plus 1. Is it okay? Right. here x1, x2, x3 are real numbers. y1, y2, y3 are real numbers. The real number system we can add, right? Suppose this one also real number, no? X1 plus y1 also real number. Add again what? That's also real number. In the real number system, the commutative property is satisfying. That means we will write here this x1 plus y1, we will write y1 plus x1 plus 1. Is it okay? Here y2 plus s2 plus 1. y3 plus s3 plus 1. So, right. So, what is the meaning of this one? This one means y1, y2, y3 is a vector addition is x1, x2, x3. So, it is your v, it is your u. Right? In the real number, right? In the real number, commutative means, or additive commutative means x plus y equal to y plus x. In the real number system, okay? These things I will use here, right? Now we will prove this vector addition is a commutative, okay? This vector addition is a commutative. Thus this addition is commutative. Okay, thus addition is commutative. Now you want to check the associative for this addition, right? Now you want to check the associative for this addition. Okay. This is the commutative property. Next, we want to check the associative. For associative, you want to take the three vectors. Okay. For associative, you want to take the three vectors. So, this is the third axiom. You want to check the axiom number 3. This one you want to take three vectors. No? Let u and one vector x1, x2, x3, and b another vector y1, y2, y3, and u b double g, no? Double g another vector xy z1, z2, z3. These three vectors belong to R3. So your claim is this one. First, think about the claim. Your claim is you want to show that it's a vector addition of u, v, double g. This is also vector addition equal u plus v. It's also vector addition. It is your claim. Okay. You want to prove this claim. Okay. So we will take the LHS side part first. Okay, u plus vector addition v plus w. Okay, right. So u is your vector x1, x2, x3. V is your vector y1, y2, y3. So vector addition z1, z2, z3. Is it okay? Now you hit this one, x1, x2, x3. This addition is this one, no? y1 plus z1 plus 1, y2 plus z2 plus 1, y3 plus z3 plus 1. Okay, right. Again, this one, another vector. This one and this one and this one. So we will write again, do the addition or vector addition here. That means x1 plus y1 plus z1 plus 1. Okay, s2 plus y2 plus z2 plus 1, s3 plus y3 plus z3 plus 1. Okay. Here x1, y1, z1 are real numbers, like as here also. Here also. So in the real number system, this associative property is satisfying. That means you can use this one, x1 plus y1 plus z1. Right? x1 plus y1 plus z1 we will write the form x1 plus y1 plus z1. This is associative property for the real numbers because x1, y1, z1 are real numbers. So, right? So, you know, here you can assume that there are three elements like this. You can add this one element, this another element, this one another element. There are three elements. I mean, you assume that z plus one is z1 plus one is one of the element. Okay. Now I will write like this. Is it okay? Suppose you add this one, you will get this one again. Okay. So what is this? This one means, right? S1 plus y1, right? Yeah. Sorry. Here S2 no. Important. It's 2. Okay. Don't worry, right? Okay, it's 2. Then here you want that 1. Here also 1. Here also 1. It's okay, right? No problem. Right. All right. What is the meaning of this one? This one means x1, y1, sorry, x1, s2, and x3. Yeah. x1, x2, x3. It's a vector addition. y1, y2, y3. It's okay. Right. Again, vector addition of z1, z2, z3. Now, this x1, x2, x3 vector means u. Yeah, it is u. It's vector addition. Okay, it is your v. Another vector addition, it is your w. Is it okay? This is your claim. You take this one, you prove this one. Therefore, we prove this claim. Therefore, thus this addition is associative. Okay. Okay, right. Next axiom, you want to check the next axiom, you want to check the identity of this addition. Okay, right. for this, you take one vector u and v. If v is your identity, then we will get again u, for the vector addition. It's minus 1, minus 1, minus 1. Usually belong to RQ. If both vectors are in RQ, then you can do the vector addition x1, x2, x3 minus 1, minus 1, minus 1. Then you again get this value u, because what is addition? It's vector addition. X1 minus 1 plus 1, x2 minus 1 plus 1, x3 minus 1 plus 1. Then you get x1, x2, x3. It is your u. Now, right now, somebody can ask, but how can you get these values, b values, right? Because it is your identity values. How we will get the identity values for this question, right? And roughly do this problem, uv. Okay, you take for u is x, x1, x2, x3, y1, y2, y3. You can assume that v equal to y1, y2, y3. Then you want to find the values of y1, y2, y3. So y1 is minus 1, y2 is minus 1, y3 is minus 1. You get three values of minus 1, minus 1, minus 1. Then this is your identity. Suppose you take this addition, then you again get x1, s2, s3, no? Because it is the identity of this one. Okay, right. Now, what is the additive addition is x1 plus y1 plus 1, s2 plus y2 plus 1, s3 plus y3 plus 1. This one equal to x1, x2, s3. Coordinate wise, these elements are equal. So therefore, x1 plus y1 plus equal x1. From this one is y1 is minus 1. Is it okay? Y1 is minus 1. Similarly, x2 plus y2 plus 1 equal s2. Coordinate wise are this element equal to this element. So y2 is again minus 1. For last values s3 plus y3 plus 1 equal x3. So the y3 also minus 1. Therefore, I1, I2, I3, all values are minus 1. Therefore, your coordinates of your identity values is minus 1, minus 1, minus 1. Right? Roughly, you can work it out and you can apply that values here. Then you get again that u. Therefore, it is your identity. Okay, right. Thus, minus 1, minus 1, minus 1 belong to RQ. Right? It's an identity. It's an additive identity. Okay, it's an additive identity. Next one. Okay, next one. You want to find the additive inverse. Okay, additive inverse. So that let you take u equal x1, x2, x3. B, right? Your inverse is b of the form minus x1 minus 2 minus x2 minus 2 minus x3 minus 2. So also belong to RQ. Suppose you add this u addition b, you can get whatever you can get. You can get this identity values, no? Let me check that one. X1, x2, x3, y1. So y1 is this one. Minus x1 minus 2 minus x2 minus 2 minus x3 minus 2. Suppose you add this 2, you'll get x2 minus x2 minus 1 plus 1, x3 minus x3 minus 2 plus 1. So then here minus 1, here minus 1, here minus 1. Yeah, because you identity, then B is the inverse of U. Okay, B is the inverse of U. Right. Somebody can ask the question like here also. What is the? How can we find this inverse? Okay, how can we find this inverse? For this we can roughly work it out. Then you can find this. Y1 is this one, Y2 is this one, Y3 is this one, like a previous one. Okay, right. We will do that part now. So okay, right. UV, no? UV. So addition. Again, you can get U. Sorry, again you can get the identity. Identity is this one. Okay, minus 1, minus 1, minus 1. Now, this is U is your x1, y, x2, x3. Vector addition, y1, y2, y3. You get minus 1, minus 1, minus 1. So, right, you take the b vectors b value y1, y2, y3. Now your claim is you want to prove that y1 equal to minus x1 minus 2, y2 equal minus x2 minus 2, y3 equal minus x3 minus 2. Okay, right. X1 y1 plus 1, s2 y2 plus 1, s3 y3 plus 1. This one equal minus 1 minus 1 minus 1. So coordinate by these elements equal to this element. That means x1 plus y1 plus 1 equal minus 1. This one implies your claim is you want to find the y1 values. Y1 means minus 2 minus x1. Is it okay? Minus 2 minus x1. Similarly, for x2, similarly for y2 values is minus 2 minus x2. Similarly for y3 values, right? That means it is B is your inverse, no? It's y1, y2, y3. It is your inverse. So y1 equal to, in terms of x1 is minus 2 minus x1. That means we will write minus x1 minus 2 minus x2 minus 2 minus x3 minus 2. This one also belong to R cube. It is your additive inverse of this U. Okay? Right. Thus minus x2 minus x1 minus 2 minus x2 minus 2 minus x3 minus 2 belong to R cube is an additive inverse of U. U means x1, x2, x3. Here we verified there are 5 axioms. If 5 axioms are satisfying, then we can say that this R cube is a abelian group, right? R cube is a abelian group, right? For the vector space, you want to check the 10 axioms. Remaining 5 axioms, you want to check. Okay. Okay, right. axiom number 6. You take one of the scalar a, right? You take one of the scalar a, then you take the scalar multiplication with this vector is s1, y1, z1. So x1, s2, s3 belong to R3. It is given but this a is u. It is given but a x1 plus a minus 1. Is it okay? Yeah. A x2 plus a minus 1 is given but a x3 plus a minus 1. You know, this x1 belongs to real number. Therefore, a x1 belongs to real number. Adding again a, this one also real number. Subtract minus 1. Again, this one real number, this one real number, this one real number. Therefore, this one belongs to R cube. Right? This one belongs to R cube. Thus, R cube is a closed under scalar multiplication. Okay. Thus, R cube is closed under scalar multiplication. So axiom 7. You take one scalar and two vectors. Belong to R cube. Now, use this vector addition is given 1 x1 plus y1 plus 1 s2 plus y2 plus 1 s3 plus y3 plus 1. Now this scalar multiplication also given 1 upon this one, then a into x1 plus y1 plus 1 plus a minus 1, a into this value x2 plus y2 plus 1 plus a minus 1, a into s3 plus y3 plus 1 plus a minus 1. So, right, the client is, you want to show that this one equal a u plus b equal u, this one your client, scalar multiplication and the vector addition. So, single idea, you can prove after doing something here, then you can get these values. Otherwise, you take this one, this values for finding these values, a scalar multiplication of u with the addition of a scalar multiplication of b. You get one of the value for this one, that value is equal to this one, therefore both are equal. Right? That means you take this one. It's very easy, otherwise take more times. So a dot u means you know that a x1 plus a minus 1 ax2 plus a minus 1, ax3 plus a minus 1. It's vector addition. Okay, a y1 plus a minus 1, a y2 plus a minus 1, a y3 plus a minus 1. Okay, now you add both, then you get again a x1, a minus 1, a x2, a minus 1, again plus 1, a x2, a minus 1, a y2, a minus 1, again plus 1, a x3, a minus 1, a y3, a minus 1 plus 1. You simplify this one, you will get say is command, then here x1, sorry, here y1, then here x1, here y1, here a, that means 2a, yeah. Here minus 1, minus 1, minus 2 plus 1, again minus 1, here also minus 1, minus 6. Here command x2 plus 92 plus 2a minus 1, here 2a minus 1, a x3 plus 3 plus 2a minus 1. No, that means this one equal to this one. Okay, this one equal to this one. That is your client. Okay, that is a scalar multiplication of u vector set b equal a scalar multiplication of u vector addition a scalar multiplication of b. Okay, now we want to check the axiom number 8. Axiom number 8. So axiom number 8. You take two scalars, one vector. So a plus u. It is general addition, not a vector addition. It is a scalar multiplication of u. So what is the value? A plus e x1 a plus b minus 1 a plus b x2 a plus b minus 1 a plus b x3 a plus b minus 1. Now your claim is this one. Sanction is a vector addition. Scalar multiplication. It is the vector addition. Here not the vector addition. Okay. So okay, you can keep this one. You can keep this one. Guys, you can move one step. Associate A, B are real number, X1 is a real number, then you can also distribute it. Okay, it's AX1 plus BX1, A plus B. Distribute over this one. Okay, right. Minus 1. AX2 plus BX2, A plus B minus 1. A plus, sorry, AX3, BX3, A plus B minus 1. Now you take this one. A dot A scalar multiplication of U. Then you get for B so add addition is multiplication. So add now what? Then you get AX1, BX1, A plus B. Yeah, minus 2, minus, sorry, minus 1, minus 2, and add 1, then get minus 1. Okay. AX2, BX2, minus 2, add 1, A plus B also there, minus 1. AX3, BX3, add A plus B, then we get A plus B minus 2 plus 1 minus 1. So this one equal to this one. That is A plus B scalar multiplication of U equal A scalar multiplication of U vector addition B scalar multiplication of B. So U. Okay. Action number 9. Okay, action number 9. Action number 9, you take A scalar multiplication of B again scalar multiplication of that vector U. Action number 9 saying that action number 9 we want to prove this condition. Okay. So this, let's take two scalar, one vector, like this, like this. So B dot U, what is the value? Bx1, B minus 1, Bx2 is defined one, defined one, scalar multiplication. Bx2, B minus 1, Bx3, B minus 1. Again, do the scalar multiplication in A. Then AB, x1, AB minus A, again at A minus 1. Or here, AB, x2, AB minus A, again at A, subtract minus 1. A, B, x3, A, B minus A, again at A, subtract minus 1. So, A, B, x1, A, B minus 1, A, B, x2, A, B minus 1, A, B, x3, A, B minus 1. This one we can write like this. You take outside AB into scalar multiplication of U, then you will get this one. Therefore, my claim is, now we put the claim, our claim. Axiom number 9 is axiom number 9. Axiom number 10. Which there is one scalar multiplication of this vector U, then you get x1 U is x1 is just 3 now, x1 plus 1 minus 1, x2 plus 1 minus 1, x3 plus 1 minus 1, then you can get x1, x2, x3. This is your U. It is your U. So thus R cube is the vector space over real number. Okay, there are 10 axioms are satisfied, then we can say that R cube is a vector space under the addition, so under that vector addition and scalar multiplication. Okay. Next exercise, let B be a vector the form xy is comma y belong to real. For any alpha of the form beta of the form in B, C one of the scalar belong to R, define it is vector addition is defined by and scalar multiplication is defined by there are 3 questions we ask. First question, prove that B says vector addition is an abelian group. It's an abelian group. Next one, verify that third question, prove that E is not the vector space over R under above two operation. Under above two operations. There are three questions. First question they ask P and the scalar multiplication, this vector addition is an abelian group. Verify that this condition is not satisfying. Prove that P is not a vector space. Suppose you prove this condition, then we can easily say that P is not vector space because it is one of the axiom of vector space. No, one of the axiom of vector space. Suppose this axiom is not satisfying, then we can say that P is not a vector space. Okay, right. For this question, we will do now. Okay. Prove that that addition is a abelian group means you want to check that five axioms. If five axioms are satisfying, then we can say that this vector addition is an abelian group. These two elements are belong to B. Two vectors in B. So addition is vector addition. This one also in B. Because this is real number, this is real number. Thus these cross under addition. For a second one, it's commutative. That if you take, let again alpha is x1, y1, beta is s2, y2 in B. So select addition. Apply means you want so that alpha vector addition B equal beta vector addition alpha. That is this is your client. beta vector addition alpha. So x1 plus h2 plus 1, y1 plus y2 plus 1. In the real numbers, it is commutative. Then we write h2 plus h1 plus 1, y2 plus y1 plus 1. So this one we will write h2 y2 h2 y2 sorry, h2 x1 y2 sorry h2 y2 sorry h2 y2 and x1 y1. So this is your beta, it is your alpha. Thus this addition is commutative. Thus addition is commutative. Okay. Next, for associative, associative, you want to prove this condition. No? Suppose you take three vectors alpha, beta, gamma, you want to prove this one. Okay, you want to prove that conditions. For that, let alpha equal x1 y1, beta equal x2 y2, gamma equal x3 y3 in B. Alpha beta gamma. Alpha plus beta equal x1 x2 plus 1 y1 y2 plus 1. Again this x3 y3. Then this addition is x1 x2 x3 plus 1 y1 y2 y3 plus 1. You take the RHS side addition. The both values are same, then this one equal to this one. Alpha is x1 x2 sorry x1 y2 x1 y1 sorry x1 y1. Here beta gamma is y1 plus y2 plus 1. Oh, x value is not here, that means x2 x3 plus 1 y2 plus y3 plus 1. Okay, right now this is your x1 plus s2 plus s3 plus 1 y1 plus y2 plus y3 plus 1. Check here, this value is equal to this value, both are equal. That is your apply. Okay. Question number 4, you want to find the identity value, right? For this alpha is, you take let alpha is x1 s2 x1 y1. Then beta you take -1 both in B. So alpha beta. Alpha beta x1 is minus 1 plus 1. So y1, y2 is minus 1 plus 1. Then you again get is x1, y1. This x1, y1 is alpha. How we get these values? So roughly you can work it out. Suppose you take alpha is x comma y, your this beta is you take alpha is x1 by 1, no problem, x1, y1, beta x, x2, y2. Then suppose you add this one, it is your identity. It is your identity. Suppose your s2, y2 is your identity, then you can again get this x1 by 1. So therefore, addition is defined by vector addition. x1 plus x2 plus 1, y1 plus y2 plus 1. This one equal x1, y1. So coordinate wise, this element is equal to this element equal to this element. From this one, we can get the values of x2 and y2. So x1 plus s2 plus 1 equal x1 means s2 is minus 1. Therefore, s2 is minus 1. Now, what find the y2? y1 plus y2 plus 1 equal y1. This one implies y2 equal to minus 1. Y is cancelled, y2 equal to minus 1. Y2 equal to minus 1. Right? Therefore, it is your additive identity. Okay? Thus, minus 1 is an additive identity. Okay? Next, you want to find the inverse. Okay. Next inverse. Alpha equal x1 y1 belong to B. Suppose you know what is your inverse? Inverse of the form, inverse of the form beta, you take beta, is inverse of the form like this one, minus x1 minus 2 minus x y1 minus 1. This one also belong to this one also belong to B. Then if you add that to the vector addition, then you get x1 y1 minus x1 minus 2 minus y1 minus 2. Then you have x1 minus 2 plus 1 y1 is vector addition. Y1 minus y1 minus 2 plus 1. So this one is minus 1, this is minus 1. This is your identity. Then what my question is, how can you find this inverse? After you can work it out, you assume that this inverse is, you take u is x1 y1 and b is the inverse is x2 y2. Now the client is going to find the x2 y2 values in terms of x1 y1. Okay, x2 y2. Then u plus b. Suppose you add this 2, then you can get the identity values minus 1 minus 2. So adding this x1 plus x2 plus 1, s2 plus s3, sorry, x1 y1 plus y2 plus 1, y1 y2 plus 1 equal minus 1 minus 1. Coordinate wise, these elements are equal, then x1 plus s2 plus 1 equal minus 1. So implies x2 equal minus x1 minus 2. Similarly, y1, y2 plus 1 equal minus 1, then y2 equal minus y1 minus 2. Okay. Yeah, y1 is this one. Sorry, x2 is this one. It's okay. Yeah. This is your y2. Okay. Therefore, it is your inverse. Okay. Thus, additive inverse of this full values. Now these 5 axioms are satisfying, then we can say that P plus select addition is a abelian proof. Okay, it's an abelian proof. Right. Next question, you want to verify that. No? Second part is you want to verify that. Right. You want to verify that. For this, you take some values, right? We assume that let C equal to 1, alpha 1 of the vector, 1 comma 2, beta is 3 comma 4. You can assume that two vectors in V on a real number. Okay, in V. So check the condition. 1. What? This one is 1 plus 3, 1 plus 3 plus 1, 2 plus 4 plus 1. So again, 5. So this one is 5, 7. Sorry, what is this value? 5, 7 or not? I think it's not 5, 7. No? Yeah, okay, it's 5, 7. Okay, right. Yeah, 5, 7. What about this value? Yes. So 1, comma 2, 1, 3, comma 4. Here this value 1, 2. This value 3, 4. So addition is defined by I think it's okay, no? So verify that. Okay, it's like this. Addition is maybe it is the correct or wrong, and we want to check that one. Here, supposed to you can take any values, but I think it's correct, no? Right, because because 1 plus 3 is 4, 1, 5. Here 2 plus 4, 6 plus 7. Is it okay? 5, 7, 5, 7. Okay, right. But it's a real number, but this case is real number. Yeah, okay. Oh, this I think this case okay, but let you put the minus 1 here, right? Let you put the minus 1 here. Put a plus 1, okay, but minus 1 I think is not bug, I think, right? Okay. Because real number, then you can put plus minus term also. Plus, put C minus 1 there. Alba say embarrassed, you can put no. So 1, 1, let this 3, 1, 4, 5, 6, no? So this is 5, sorry, minus 1. This is minus 5, minus 6. Next, minus 1 times 1, 2, plus minus 1 times 3, 4. So what is this? This is minus 1, minus 2. It is minus 3, minus 4. Now at this addition minus 1, minus 3, plus 1, minus 2, minus 4, plus 1. Then you get minus 4, 1, minus 3, minus 6, 1, minus 5. They are both are not equal, no? For negative case is not possible, but positive is okay. Therefore, this true means for anywhere else, but yes, negative condition is satisfying. Therefore, C scalar multiplication of alpha plus expectation of beta and C scalar multiplication of alpha vector addition C scalar multiplication of beta is not satisfying for this case. Okay, for this case. Therefore, is one of the axiom in the vector space. Therefore, last question your answer is it is not a vector space because one of the axiom is not satisfying. Therefore, it is not a vector space. Okay, this axiom is not satisfying. Therefore, it is not a vector space. Okay.